In the past, we've talked about methods to normalize our database to reduce data redundancy and decrease bugs. One of the downsides to normalizing our database is that there can be performance problems as we interact with this data at scale. We may have to join several tables to get the data that we need in one query, and performing calculations on tens of millions of rows can take a significant amount of time. When we run into performance problems with large amounts of data, we need to find other solutions for how we can store our data. In this video, we'll discuss database denormalization and how it can be used in your application to improve performance. Hello developers and welcome to the PHP Architect channel. If this is your first time here, my name is Scott Keck-Warren, and on this channel we discuss a wide variety of topics related to the PHP ecosystem. Make sure you subscribe so you can get our latest videos when they're published, and make sure you hit that bell so you get notifications when they're released. When we normalize our database tables, we go through an iterative process to design our database tables to remove data redundancy by keeping exactly one copy of each piece of data in our tables. Denormalization is a process we use on normalized data tables to increase read performance at the expense of some write performance. This is done by adding redundant copies of data or by grouping data in ways that it can be faster to read later on. When we denormalize our database, we might add columns with derived data, create tables that split an existing table across logical boundaries, or create aggregate data. We may either use database management system denormalization or database administration denormalization. Database management system denormalization is when our database management system provides support to denormalize the data automatically, while database administrator denormalization is when we have to manually store and update the data logically. So denormalization is a great solution for any kind of data that gets updated infrequently or data that is part of a report that needs to display very quickly. Some example techniques including keeping count of the many elements in a one-to-many relationship by storing the count as a column in the one element, adding attributes to a table that are copies of data from another table that are routinely joined together, and creating summaries of data. A normalized database gives us a lot of performance out of the box, and denormalization can be a case of premature optimization that overcomplicates the structure of our code for little to no gain. I recommend not jumping right into using denormalization when it may not be needed. We want to use denormalization only when we start to experience performance problems in our application that can't easily be solved by adding more memory to the database server or more processors. Do you want higher clarity in production but don't have the time to earn your degree in observability? Me too. Forget logs, metrics, and traces. HoneyBadger Insights is built around structured events. When you send your application logs and other events to HoneyBadger, you'll unlock the power of HoneyBadger's powerful new querying language, BadgerQL. You can then use BadgerQL to ask any question about your data, convert any event into a metric, and chart your metrics on a custom dashboard. You can do all of this on HoneyBadger's free plan as part of their comprehensive monitoring suite, which includes error tracking, uptime monitoring, status pages, and more. Speaking of error tracking, did you know that an error is really just a first-class event in HoneyBadger? In fact, you can use Insights and BadgerQL to explore all of your existing HoneyBadger data in new ways. It's pretty cool. Give it a try today at honeybadger.io. That's honeybadger.io. Now, there are several techniques that we can use to structure our denormalized data. We're going to cover some of the techniques that I find the most helpful, but this is not a complete list of all of them. The first technique is to create a redundant column that pre-joins our data for cases where we commonly join one table to another to get a specific column. For example, let's say we have a charges table that is used to track financial charges for specific customers. For this example, we'll keep it really simple, and the customer table will just track the name of the customer. Now, we commonly join the customers table to the charges table to display what customer is associated with the charge. And to improve performance and prevent the join, we can add a customer name to the charges table that is updated whenever the customer's name is updated. Another option is to split the table into multiple smaller tables so they're faster to query and to manage. We can either do this horizontally or vertically. When we split a table horizontally, we make multiple duplicate copies of the table with the same columns, but then split the data based on customer, region, location, department, or any other kind of logical separation. For example, our charges table may have reached the point where there's too many entities for us to be able to easily perform actions on all of the rows at once. And we can generate 10 tables for the various regions we service in order to increase performance. We can then either stop using our charges table or perform double entry, but these region-based tables are going to be much faster to query because we're only working with a smaller subset of our data. When we split a table vertically, we keep the same number of rows, but split the columns into different tables. For example, going back to our charges table, someone went and added a bunch of blob columns to our table for supporting evidence, but they're really used in like less than 1% of rows, and it's causing a performance problem. We can easily vertically split this table into a charges financial table and a charges support table, so we can keep the financial pieces fast without having to worry about loading all of these blob columns into memory every time that we need to read the table data. The third technique that we're going to talk about is adding derived columns. When we add a derived column, we create columns that are derived from other data. I know it's kind of self-explanatory, right? For example, we may need to display the total charges customers have generated for the current year. To generate this data, we can, of course, perform a join between the customers and the charges table, filter it down to just this year, perform a group by, and then output the results. Again, we might have some performance issues as this table grows larger and larger. To increase performance, we can add a specific column to our customers table and then store the results there to increase the query speed. And then we only have to update it once or twice a day. Next, we get to mirrored tables. When we create a mirrored table, we create a full or partial copy of a table, but stored in a specific location that is specifically optimized for faster query performance. For example, we may have a separate database server set up to perform analytics on our data. By having it separated, it can then perform faster and won't affect the workload for the rest of the system. Finally, we can use materialized views, which are basically a result of a query. These are typically queries that aggregate data together and can either be generated manually or using built-in database management system support. An example of this is we could create a materialized view that keeps track of the year total to date by customer and then update that every so often, but it just acts like a normal table. If your database management system doesn't support materialized views, it's very easy enough to implement by creating a cron task that regenerates the data. So now that we have a basic understanding of how to store the data in a denormalized fashion, you might be wondering how we can generate this denormalized data. Depending on your needs, you can have the data generated for the denormalized data using scheduled jobs, using a database trigger, or even inside your application's internal logic. A lot of it is going to have to do with how real-time you need that denormalized data to be. Are you happy with it only updating once a day? Then cron is going to help you. Do you need the data to be up to date immediately? Then event sourcing might be the right fit. We do a combination of techniques depending on what we need for each piece. As a recap, database denormalization is a process of creating redundant copies of data to improve read performance. You should only use it when you absolutely need it. And there are several techniques on how to create denormalized data. I hope you enjoyed our video. If so, make sure you subscribe, comment, share, and like, as it does help others find our video. Are there topics that you'd like to see us cover? Let us know in the comments section below, or send me a message on phpc.social @ScottKeckWarren. Are there topics that you'd like to see us covered? Let us know in the comments section below, or join our Discord and let us know in the Discord. We would love to hear how we could help you, and it always brightens my day when I hear from a fan. This is Scott Keckwarren for the PHP Architect YouTube channel signing off and reminding you to keep watching, keep coding, and keep reading.